So thanks everybody for coming this evening. I can't see most of your faces, but I assume that there are some people here I've seen before. It's good to have you to be all together again. And as Sheila said, you probably know me as the former curator of the Rice Museum. And I'm currently sort of in between positions due to having recently had a baby and the COVID nonsense. But I am very happy to have finished this book and to be sharing it here with you. And let's take a look at what's here. So, you know, you pick up a book, you start with the cover. And this, I see someone said something in chat. Oh, okay, sorry. Not about me. So this book is about, as the title says, the rocks, minerals, and geology of the Pacific Northwest. It's meant to be a field guide. So not necessarily something you read cover to cover, but something that's a reference for whatever topic is kind of on your mind or something that you're interested in identifying. So on the front cover, we have a lovely picture of the Painted Hills. At the bottom, we have some minerals and rocks, some of which are currently on display at the Rice Museum. And then I wanted to draw your attention to the back cover, which is a picture of a polished opal from Opal Butte, also something in the Rice Museum's collection. And this is just a little goofy aside before we get into the book, but in addition to doing the writing and making figures and things for this book, almost all of the photography is original for the book. Most of it was done by either me or my co-author Jacob. There are some macro photos that were taken for us by somebody who knows how to do macro photography. And then there are a few photos that we had to source elsewhere because we just didn't have time to take pictures of every single thing. But when I took this photo of the opal on the back cover, I was taking it just to show what a play of color in a precious opal looks like, because it's very pretty. And then, of course, we submit all of our images to, you know, after the book is written and everything, we submit everything to the publisher, and they have a layout person who puts it all together. And this person selected this image for the back cover. And when I first saw it, the thing that really struck me about it is, can you advance? There we go. It looks almost exactly like an opalized map of the West Coast, which is an unintentional Easter egg. So you've got, you know, the curve of California, Baja down here, here's Oregon and Washington. If you go back and look, you know, here's your little Baja, here's the Columbia River, you know, here's the top of Washington, Vancouver Island, that kind of thing. So that's your fun little throwaway Easter egg for the back cover of the book. Now, let's see what's actually inside. So there are several chapters. We start with an introduction to some basic concepts in geology and the setting of the Pacific Northwest. And then there are chapters to help you identify minerals and rocks. I'll skip these for the moment. Looking at structures and deformation in rocks, looking at landscapes and geomorphology. And then the last chapter is called Telling the Story, and that is a narrative of the geologic history of the region from, say, about 1.5 billion years ago to today. I see there are 2 new messages. Oh yeah, I see Carol has mentioned that she went to the Rice Museum to buy it yesterday and they didn't have it. They do have it, but there was a weird snafu with the publisher where they charged them too much for the books, so they have to like wait to get the charge fixed before they can put them on the shelves. I'm not really sure what's going on there. Hopefully they'll get it sorted out. And yes, I see that Gary has linked to the book on Amazon. You can purchase it, as they say, anywhere books are sold, through Powell's, through Amazon, from Barnes & Noble. If you have a favorite indie bookstore you like to support, you can use the website IndieBound. I'll put that in the chat, INDEBOUND, and that helps you order the book through that bookstore, so they get the revenue for that. So really, any way you like to get your books, you can get this one. So thanks everybody for promoting that. So let's, kind of go through the book to take a look what's in these different chapters. We start out, as I mentioned, with an introduction to general geology background, which most of the people on this talk are going to be very familiar with this stuff. But this book is meant to be something that anybody, pretty much at any level of interest in geology, can pick up. So it has some of the very basics, like what is the Earth made of, what is the geologic timescale, up to more nuanced details about some of the geologic features and information that you can find. And the goal of the book is to allow the reader to be as detailed or as surface level as you want. And also maybe for people for whom it's been a while since you've read about or thought about some of the big picture stuff, this is also a really good place to go with, like, well, this is the kind of thing I really should know, but I'm not really sure I can explain it that well. And so you can kind of go back and use this as a reference. So we have, of course, things like the basic compositional layering of the Earth and what plate tectonics are and different plate tectonic settings. And you may notice that this diagram looks very familiar. The diagram is meant to show just a general look at what convergent and divergent boundaries and transform boundaries look like, but it sure looks a heck of a lot like a diagram of the coastal region of the Pacific Northwest. And there's a reason for that, which is that one of the things that makes the Pacific Northwest so fascinating is how much it is a living laboratory for ongoing active tectonics for so many different processes that are packed into such a small space. So you can see things that are sort of the cornerstones of Geology 101 textbooks and basic geology education, where you can just drive a couple hours and go see it. Whereas someone like me, when I was first studying geology in Massachusetts, all of these things like volcanoes and subduction zones were just a picture in my book. And I had to imagine it. And the very first time I came out to Oregon and I actually saw the active landscape looking just like the pictures that I had studied, I was absolutely blown away. And it was one of the things that made me fall in love with the region. So not only is it really cool to get to know the geology of the world around you, but folks in Oregon and Washington are especially lucky because not only are you getting to know your local area, you're actually getting to know some foundational, fundamental, big picture geologic concepts that get to the heart of how geology works in the world. So it's a very lucky place to be living and be doing Oregon geology. Also, one quick note, the images in here, I wanted to show you pictures from the layout of the book because just so you can get familiar with how it looks, but I had to use the digital layout files that they give the authors, which are slightly low resolution, so people don't like get their hands on a copy and like pirate the digital images or whatever. So there are some images like this where that'll look a little bit blurry, but that's not true in the printed book. They're crisp and sharp in the printed book. So just wanted to point that out and reassure folks. So besides things like the structure of the Earth and plate tectonics, there's also some information about the geologic timescale and how it came to be and sort of how to read it and use it. And beyond those basic geology concepts, we also look at the makeup of the region that we're talking about. So the book focuses on primarily on Oregon and Washington. And we've split, so here's obviously Oregon down here, Portland, here's Seattle, Columbia River. And we've split the region into a number of physiographic provinces that are referenced throughout the text. So up in the northwestern corner, there's the Olympic Peninsula going down into the Coast Ranges, which is, of course, where you guys will be having your field trip soon. Way down in the bottom western corner of the Klamath Mountains. Coming up again, we have the Cascades Range heading into the North Cascades, and then, of course, the Willamette Valley and the Puget Lowlands, which are sandwiched in here. Headed out to the east, we have the Okanagan Highlands above the Columbia Basin. Then we have the Blue Mountains, which includes the Wallowas and the Ochoco's. down to the high lava plains. Bend is sort of right here. This includes the Newberry crater area, Basin and Range, which includes the Albert Desert and Steens Mountain. And then down here in the very remote southeastern corner, we have the Waihia Hills. And many folks here are a well-traveled bunch, but if you, you know, there are places here you haven't been, we have sort of descriptions of the geography and very basic rock types that you'll find in some of these areas. So these pictures, for instance, are contrasting some of the landscapes that you'll see on the western side, which are very rugged and full of trees and water and clouds. Well, of course, there are clouds in this picture too, but with some of the eastern landscapes, which are much drier, you know, have different rock types and sort of different features and things. So this kind of gets you oriented to what places sort of look and feel like, not necessarily what their underlying geology is, but what things you can expect when you are driving around and looking at stuff. And from that big overview, we go to our next chapter, which is the minerals chapter. And this is intended to help people identify minerals that you may find. So we, of course, talk about mineral properties, physical properties for identification, like habit and hardness and cleavage and luster. One of the things that was a big challenge in this book was deciding what level of vocabulary to use to be, you know, you don't want to be so generic as to be completely vague, but one of the challenges about learning and teaching geology is how much specific vocabulary people use. So we tried pretty hard to thread the needle on that and introduce the words that matter and use more sort of vernacular for things, for concepts that can be explained in a slightly different way. So you may be used to seeing crystal habit names that have like acicular instead of needle-like, but we wanted to make it a little more approachable so people didn't feel like they were just getting lost in the words, even though there are a lot of words. And beyond some of those properties and things like what's the difference between a crystal and a gem and a mineral and all of that stuff, I also included some information on things like how to tell whether the thing you're looking at is even a crystal in the first place. I know when I taught, when I was a TA for geology, that was one of the biggest struggles, was getting people to recognize whether the thing they were looking at was a weird splotch or whether it was actually a mineral. And that kind of information was something that in my experience, in my formal education, was never written down. It was something that was passed on orally in field settings or in lab settings. And so I wanted to, one of the things I really wanted to do in this book is include some of that sort of oral geology teaching tradition in a written format that anybody can reference. So that that's what this is, this section here. And the minerals are organized by their chemistry and physical structures. So in some senses, it will look a lot like a mineralogy textbook, although it doesn't quite go into all of the details of something in a mineralogy textbook. And this is an example of one of the situations where you can go into as much detail as you want. So if you are really fascinated by the atomic arrangement of the structures that make up different categories of minerals, the basics of that information are here for you. But if that totally makes your eyes glaze over, you don't have to worry about it at all. You can just keep going. I'm going to give you an example of some of the entries that you'll see in the framework silicates. Silicates are really important because they make up over 92% of the minerals in Earth's crust. So like they're everywhere and something that you would want to be familiar with if you want to be able to identify minerals. And framework silicates are some of our most common, like plagioclase feldspar. I'm going to pause here because I saw that somebody said something in chat. I'm going to leave some of these questions to the end. They're good questions, but I want to get through part of this. So plagioclase feldspar. I'm sure that every person in this Zoom meeting has picked up a rock like the one that you see on the top right-hand part of the screen, sort of a dark grayish, brownish ground mass with some white blocky crystals in it. That is in fact an andesite from Mount Hood, and the white blocky crystals in it are plagioclase feldspar. Plagioclase, so if silicates make up 92% of all minerals in the Earth's crust, feldspar, particularly plagioclase, makes up about 50% of that. So it's a big deal. It's a lot harder to find a rock without plagioclase than it is to find a rock with plagioclase. We want to talk about how to identify common things, in part so you can have a better nose for when certain things are uncommon. So here's some pictures and information about some of the common ways that you'll see feldspar. But one of the other reasons that we in Oregon particularly like plagioclase feldspar is because it's also the state gem. So under certain circumstances, basically feldspar growing in a magma chamber very slowly over a long time, it grows in a transparent or translucent instead of white opaque sense. And then if you add just a little bit of copper to the mix, you get these beautiful yellow and red and green colors and shimmery schiller. And you take, one of the most dead common minerals on the face of the planet and turn it into something really beautiful and spectacular that's emblematic of the region and something that's special to the area. So that's one of the reasons that plagioclase feldspar is one of my very favorite minerals, because it has this huge range of appearances and significance. And many of you may also enjoy agates. Oregon, of course, has quite a lot of them. When I was picking specimens from the Rice Museum collection to photograph, you could have made a whole book. It was so hard to figure out what to include for photographs for this entry. But the purists among us will note that agate and chalcedony are really rocks and not minerals, because they're an intergrowth of two minerals called quartz and mogonite. But I included them in this section with the other SiO2 related minerals like opal, which of course is mineraloid, and quartz, so that they would all kind of be in the same place and people could learn how to compare among them. So we've got some polished stuff and some rough stuff, and how to identify those different things. If you look at a list, just a plain old list of what minerals are found in Oregon and Washington, you'll get over 600 different varieties, or 600 different mineral species rather. And so one of the challenges in putting this book together was figuring out what to include and what not to include. And the guiding principle that I used was to include things that are very common, so things that people are likely to see when they're just kind of out and about. Things that are very emblematic or special to the region, and things that are rare and interesting for a particular reason. But I also chose to stick to things that you would be able to see either with the naked eye or with only very minimal magnification. If you've ever known someone who's into microminerals, it's a fascinating hobby where you can get all kinds of very strange and unusual minerals that are 2 microns across. But I figure most people who are going to be reading this book are not going to have like a super high-powered microscope to be looking at their finds. So I stuck to things that were big enough basically to find with the naked eye, and also things that could be found at or near the surface rather than having to dig and do other stuff. So this layout basically shows kind of 2 ends of that spectrum. So one of the minerals we talk about is clay minerals, another super, super common and important group of minerals. And besides just being able to identify when something's clay, it's also interesting to note that one of the reasons that people really like clay rocks is that they're very good at preserving fossil impressions. So if you are the kind of person who's interested in looking for fossils, you would maybe try to go find a clay deposit. So this is an example of some root fibers in paleosalt, a clay-containing soil. And then on the other end of the spectrum, we have these blue minerals, Pentagonite and Cavensite, which are extremely rare. They've really only been found in 2 localities in Oregon in any significant amount. And one of those localities in the Oahe Dam has actually been destroyed. So it's cool, it's bright blue, it's big and you can see it, but it's really rare. So it's if you happen to find the next outcrop of it, that would be like a really big deal. So that would be a cool thing to kind of keep your eye on. And I think I mentioned that I ended up choosing 62 different minerals. So you'll get things you've never heard of before to things you've definitely heard of before, like gold, and kind of everything in between. Now, I mentioned earlier on that the minerals are arranged, they're organized in the chapter by their chemistry and structure. But if you're just walking around in the field and you pick up a rock, you might not necessarily say, this is a framework silicate, or this must be an oxide. And so it might be difficult for you to look up your mineral that way, which is why I have included a number of tables after this chapter that list minerals by color and hardness and color and habit. Basically, so if you pick up, say, a green mineral that has a hardness of, you can scratch it with your fingernail, you can go over to the green mineral section and say, what's less than my fingernail? Talc, autunite, and chlorite. And then you can look up those 3 entries to help you narrow down on what your find is. And the same thing with color and habit. So like a green elongate mineral versus a green stubby mineral or a green round mineral. So it helps you take the properties that most people first notice when they pick up a mineral and narrow down on what entries to read to figure out what their mineral actually is. And I'm actually going to pause right now and see if anybody has any questions before I continue.
Are you able to see the chat box with the questions, Leslie? And do you want to address these now or wait?
Yes, so I see there are a couple of questions. So the question for me is, are there plans to publish this book digitally? Not as far as I know, not presently. I don't know. But, and then there's a question for everybody about what are your favorite geology, rock, and mineral mobile apps. I will leave that maybe for people to discuss at the end. I don't know if anybody has any other mineral questions right now. If not, that's okay. We can save that for the end and we will move on to rocks. This is an image of columnar jointing in the rattlesnake tuff. Before I moved to Oregon, I didn't know tuffs could have columnar jointing, but here we are. And the rocks chapter starts with, again, some basic geology. What is an igneous rock? What is a sedimentary rock? What is the rock cycle? How do rocks get made? And sort of the 30,000 foot view, something everyone here is very familiar with, I'm sure. And we also look at a generalized geologic map of the region that's broken down into the very, very basic rock types. So we have igneous rocks, which are in warm colors. We have your oranges and your reds and some of your browns. Sediments and sedimentary rocks are in blue and sort of light tan. And then metamorphic rocks are green. And we've got some ultramafic rocks scheduled in here and some mixed lithologies, which are also kind of green. And if you look at this map for a little while, you might notice something interesting, which is that it actually looks a heck of a lot like this physiographic provinces map that we started out looking at in the first chapter. And that's not an accident. sorry. We live nowhere near an airport, but for some reason there's like this massive helicopter flight path that goes over our house, and so we get these like low flying, loud helicopters. I'm sorry if that's drowning me out right now. But anyway, back to the story. So the fact that these maps look very similar to one another isn't an accident. The underlying geology of these different provinces is one of the major things that gives each province its basic characteristics. So in the map on the left, the lines are drawn based on sort of geography and physiographic expression, like where is the edge of that mountain range, where is that valley, where is the dry part versus the wet part, and so on and so forth. And over here, this is a bedrock map, sort of what's lying underneath it. And again, that's one of the reasons that studying geology in Oregon, Washington is so cool, because the combination of the properties and qualities of the underlying bedrock in conjunction with the ongoing active tectonics creates these zones that are, I wouldn't say predictably different from one another, but you can see how the things that people enjoy about each area come from the properties of the tectonic activity in the bedrock underneath. It's one of the reasons I think it's pretty cool. So let's look at some of these rock entries, and we'll start off with basalt, which is not boring in my opinion. It's fantastic. And I mentioned that some of the photos in this book came from a GSOC trip I went on. This picture of the Palouse River Canyon was not actually on the trip. It was when I was leaving the trip. I went from the Wallowas to Seattle, and I decided to go by Palouse Falls on the way. So I got to see this really cool shot of, you know, all the different layers of Columbia River basalts, plus some of the later smaller eruptions on top, and of course the erosion of the canyon and all that stuff. Anyway, really neat, totally recommend it. And we can see some images of basalt generally. So we have your, you know, your sort of crummy gray basalt outcrop, blocky basalt outcrop. We see vesicular basalt. We see some cinders with lots of different colors. And so this, so the rock entries talk about texture, rock texture, and rock composition, and also some of the major features in the region that are made by or influenced by certain rock types. So, you know, the Columbia River Gorge and Haystack Rock on the coast and Silver Falls State Park and all of those things, to kind of give you an idea of the relationship between the rock type and the land. And when I, again, kind of going back to my time as a TA, one of the things that was most challenging to do was to get people, when they pick up a rock, to look beyond the color of the rock. You know, everybody wants to say, oh, that's a green rock, therefore it must be this, or oh, that's a red rock, therefore it must be that. And, you know, to use color to help you understand what's going on, but in order to identify it, you have to look past it. So for instance, if you look at this entry on tuffs and you look at these three rocks right here, you have something that's kind of green and white, you have something that's kind of tan and white, and then you have something that's pinkish with these like red and black things. And these are all, broadly speaking, the same kind of rock. They're tuffs that are emblematic of, and the reason that they're all considered under the umbrella of the same kind of rock is because they are rocks that form from violently explosive eruptions. So part of the other point of this chapter is not only to get you to identify the rock, but to see the story that led to the creation of that rock. Basically learning how to read that story yourself by looking at the textures that you see and how that's related to the process that made it. So learning to look at a tuff and seeing in your mind's eye an enormous volcanic explosion with, you know, pyroclastic debris and death and destruction and all that stuff is, you know, a fun storytelling thing that you can learn to do with rocks. And we want to be able to look at things, again, with the basalt, we want to be able to look at and identify rocks at the small hand sample scale, but then also look at the landscapes that they create. So here, for instance, is an image of tuff spires at Smith Rock State Park, which I'm sure you're all very familiar with. Just like in the minerals section, so the rock section is organized by sort of, igneous, sedimentary, metamorphic, and different textures and this and that. But if you're a newbie rock identifier and you pick up a rock and you're like, well, I don't know if it's igneous or I don't know if it's sedimentary. There are some flowcharts that let you make a few simple observations and then asks you questions to guide you to some options. So it's kind of like a choose your own adventure book for your rock. And it will lead you to, based on the questions that you read and answer, it'll help you narrow down again to 2 or 3 different entries that you can go read more in detail, so you can help identify the thing that you're holding. There are also, in the rock section, a couple of short interludes about fossils and meteorites. This is not in any way meant to be comprehensive. There are many wonderful fossil books, and I am not a fossil person, so I can tell you whether something is a fossil, but I can't really tell you like anything about it beyond that. I don't know anything about things that used to be alive. But often at the museum, I would get people who would come in with some funny rock, and they'd be like, "Is this, a petrified foot, or is this a bone, or what is this?" So this section is about how to figure out, how to recognize a fossil shell or a piece of petrified wood or a bone or something like that. And then if you want to know any more about it, you'd have to actually go to a paleontologist. But just to help you basically make that first pass identification. There's also a similar section on meteorites. The next chapter on structures, I'm actually going to go through pretty quickly, because it's just better to read this chapter than to talk about it. But so of course we have, we can now identify minerals, we can identify rocks, which is what happens when a bunch of minerals get together. And then rocks, of course, aren't just like little chunky things that lie on the ground, right? They're part of larger formations that are make up the architecture of the world underneath our feet. And they're in different formations, like big lateral formations or blobby formations or something, and those formations interact with one another in a sort of architectural or geometric way, and they are moved relative to one another by plate tectonics. So the shapes and arrangements of rock formations and the structures and deformation structures that they make are also part of learning how to read the story in a rock. Not only do you need to know what the rock is, but you can also see information about how the rock got to where it is based on the structures that you can find. So the beginning of this chapter shows something called pencil cleavage in slate, which is what happens when you take a mudstone and deform it in a whole bunch of directions. And so when it breaks into these long shards. And then here's also a picture of what happens when you take a rock and push it way far down in the crust and heat it up a lot and start to deform it. Instead of breaking and cracking, it will start to bend and ooze and make these cool swirly folds. This part of the chapter is about faults. So faults are, of course, where earthquakes happen, right? And this is an example of how to figure out whether you're looking at a fault. So looking at an illustration, kind of an idealized block diagram of an offset bed with a hanging wall and a footwall, and then looking and seeing at what that looks like in real life. So this is in the John Day Formation, you see these sort of stripy greenish beds, and then there's this offset darker bed, and you can see the trace of the fault plane right here, and here's the hanging wall that dropped down. We're gonna go beyond the structures chapter to the Landscapes and Geomorphology chapter. And I didn't write this chapter, this was Jacob's chapter, but in some ways, I think many people will find this one of the most interesting chapters in the book. Because for a lot of people, the kinds of questions that you can answer from this chapter are the kinds of questions that got people interested in geology in the first place. So for instance, when you go to the coast and you see these really cool shapes and headlands and sea stacks and arches and things, it's interesting to know what kind of rock that is, but you also just want to know, like, why does it look that way? How did that shape happen? How did that get there? And so this chapter in Sculpting the Landscape is showing you feature identification, like what are these things called, what are their names, and then it also discusses the processes that form them, so you can kind of see the ongoing process in the landscape around you. And that's important not just in really dramatic landscapes like the coast, but it's also something that you can see in littler ways all around you. So if you've ever been hiking and you've been on a hill slope and you've seen a bunch of trees that look like they're all kind of curved in the same direction at the base, and you've wondered what that's all about, well, that's an example of something called soil creep, which is a very slow landslide in motion. And that's something that you might be interested to know if you, say, just got tired of people and the world and you wanted to go become a hermit and build your own cabin in the mountains. You wouldn't want to build your cabin in the mountains on a hill slope that looks like this, because the soil is very slowly moving down over time. So if you built something on it, your foundation would get messed up in not too long. So in addition to looking at the ways that geology can be sort of big and inspiring and cool, we're also looking at the smaller ways that it can be relevant to our lives. And this picture on the bottom was intimately relevant to my life for a while. This is a picture of a fresh landslide along Newberry Road, which connects Skyline with US 30 over the Tualatin Ridge. And I used to use this road to commute home from the museum every day. And then when it washed out, it took like a year to repair, and I had to go down Highway 26 instead. And I was really pissed off about it. So I figured I should probably include a picture of the destructive power of fast landslides in here as well. And in addition to seeing rocks and formations that are talking about that illustrate processes that are ongoing today, we can also look at landscapes and formations that tell us about the past. So we all know, of course, that ice ages are a thing. And when the Earth is in ice ages, there's a lot of snow and ice that forms glaciers. But of course, we are in an interglacial period, and they're not there anymore. So if all the ice melted, how do we know that it used to be here? And the answer is we can look for geomorph features related to the formation and movement of glaciers. So some of you may be familiar with some of the words like cirques and horns, and hanging valleys and tarns. So this section not only gives you the vocabulary for like what these things are called, but it also talks about how they relate to the process. So you can be out walking around and realize, like, hey, this bedrock has these parallel scours. I wonder if those are glacial striations. Was there a glacier here at one point, maybe? And then you can look it up and find out you were right and you were really smart. So that's what this chapter is kind of all about, learning to see those superficial processes that are sculpting and eroding the rocks after other processes formed them and brought them to the surface. And then the last chapter, called Telling the Story, has basically some more narrative background information. So the purpose of the feature identification chapters is to help you not only figure out what things are called or named, but also to, as I mentioned before, learn to see the story in them. Like, why, this is a basalt, why is that interesting? What does the fact that there is a basalt here, what can that tell me about the region that I'm in or the history of this thing that I'm standing in front of? And when a geologist goes out into the field, the first thing you do is you look at stuff, right? You use your eyes to get a first pass understanding of what is all around you. And you can figure out quite a lot just by looking at things and hitting something with a hammer and then looking at it again. But that's not all there is to geology, right? There's like lasers, and you can date things with radiometric dating, and you can look at the chemistry of different rocks and look at thin sections and things. So by using these various scientific techniques, thousands of scientists over many decades have managed to get more information that gives a fuller picture of the story of our region. And so this chapter is about how that process works, basically how you integrate information into a narrative, and then it also gives a narrative of the geologic history of the area. And I see I have a question. Where is the site depicted on page 290? That is a good question. That was a picture that Jacob took, but if I look it up, I might be able to tell you. See, I'll get back to you on that question. I'm pretty sure it's in Washington State. I'm pretty sure it's on the Olympic Peninsula. But I can look at my notes later and see if I can find you a better answer to that. So what's in this chapter about telling the story? We start way back before Oregon and Washington even existed, when the Pacific coastline started in Idaho and the edge of Nevada, and talk about the process by which the continent grew to include what is now Oregon and Washington through the process of terrain accretion at the subduction zone. And the way that this section works is we talk about theory, but then we also talk about the particular formations or general localities where these things are evident. So it's not a field guide like, it's this outcrop on this road and turn right and go 20 meters or whatever. It's not that detailed, but it gives you enough information that if you're like, oh, that's really cool, I'd like to go see that. It has formation names or regional names that you can then easily look up more detailed information about how to actually like go see the thing that you're interested in. Looking at some of the regions of accreted landscapes and the special rocks that form from in subduction zones and those related processes is the beginning. We move on to kind of the second phase of growth of the Pacific Northwest, which is the many different phases of volcanism, looking at some of the older volcanism, like the ash beds in the Turtle Cove assemblage in John Day, and of course, our more modern volcanoes like Mount Rainier. We also look at some of the both old and new structures, like the Mylonites and the gneiss domes in the Okanagan Highlands, that's in northeastern Washington, and the modern brittle faulting in the Basin and Range area, looking at Steens Mountain, Albert Desert, that kind of thing. There's a little bit about the Cascadia subduction zone in there too. And then we come to an end, and the end of the book also has some resources for working in the field or more places to look for information specifically about finding field locations and other things to explore. And that is the story of the book. This is a true color image, by the way. It's not a false color one.
Wow, beautiful.
Does anybody know where it may be?
No.
No? Blue Basin in the John Day area.
Oh, wow.
So this is not a picture I took. This is one of the pictures that, one of the few pictures that we got from somebody else who goes and takes cool pictures of this kind of thing. But if you've never been out there,
Yeah.
The rocks really can be quite vivid, especially you can see that there's water running through here, right? So this is sort of during or right after a rain, which of course makes the colors really pop. But if you notice that the water looks kind of greenish, that's not fake. So this water is picking up quite a lot of sediment from these very green beds, and the water actually is running a very green color. When I went out to look at this area, I wasn't there when it was raining, but it had rained a couple of days before, and there were still a lot of puddles. It was really weird to see these like bright turquoise green puddles in the middle of a very dry, dry area. So it's a cool and funky place. Any questions?
Very cool. Yes, this is a good time, folks, to, it looks like you've covered all the questions that were in the chat box. So this is a good time for folks, if you want to unmute yourself and ask a question, this is a good time to do so.
I see someone has raised their hand. I don't see your name though. I'm not sure why I can't see your name. But you have curly hair and glasses.
Okay, that's got to be me. I noticed that you have an interesting picture. I didn't notice what the page number was, but it was a rattlesnake ash flow tuff. Columnar jointing, and I thought that the columnar jointing only happened in cooling basalt flows. Is the physics that caused this jointing in the ash flow tuffs? Isn't it? It must be different from for the physics that causes the jointing in basalt flows, right?
No, same deal. So jointing can happen basically in any fairly homogeneous, fairly hot deposit that goes through a cooling process. So it can happen in basalt, it can happen in andesite, it can happen. So the reason that I was surprised when I first saw this in the tuff is because you think of tuff as like a particulate, right? But welded tuffs are a little bit more similar to lava flows in some respects. So with a lava flow, right, you have molten lava that leaves a vent and flows over the surface. And then you have this kind of, big pancake of stuff that cools over time. It forms the skin on top and then kind of cools in the middle. The columnar jointing that forms is related to the volume change that happens between the hot molten stuff and the cooler solid stuff. And how that, because it doesn't cool all at once, it sort of cools sequentially, basically how things pull away from one another as they cool. And when you have a welded tuff, you have particles of ash and pumice and rock that are ejected from a vent as particles that fly into the air. But if they stay very, very hot and they land together when they're still very, very hot, they'll sort of melt into one another and they'll weld together. And the resulting texture can actually look quite a lot like a lava flow, especially if you don't just have particles that go up and then they land. Sometimes you can get what's called an ignimbrite, basically where you have sort of a cloud of fast moving hot particles that rush down the side of a slope. And basically the major way that you can tell that these things are tuffs rather than lava flows is to look for pumice fragments, which you only see in those very explosive kind of eruptions instead of flows. So if you have particles that are so hot that they don't totally remelt, but they're like gooey instead of being hard particles that run into each other, you basically have those same conditions as you have with a lava flow, where you have sort of a big pancake thing that's very hot and it's cooler on the top and cooler on the bottom and very hot in the middle, and it slowly cools and shrinks as it cools, and you get the columnar jointing.
This is in Washington State. Are there many of these in Oregon?
The rattlesnake tuff is in Oregon. It's an Oregon formation. Again, this is one of Jacob's photos, so I'm not sure where exactly this outcrop is, but it's in Oregon.
Thank you.
I believe it's 6 million years old, if that helps. Any other questions?
There's a comment from Carol Hassenberg that I would definitely heartily agree with. She loves the educational focus of the book, and it trains you to see this with your eyes. And I think that's wonderful. That's what I've always noticed about your displays at the Rice Museum, was that they were very focused on education and complement what I was teaching in the classroom. I think I'm going to require students to buy this book for my next Rocks and Mineral class.
Well, I think that'd be fantastic.
Because, every time you always have the issue of how do I explain this to somebody who has, how can I get them up to speed with some of the basics like plate tectonics? You have to start plate tectonics. You have to talk about it anytime because it's so central to all of geology. And I think you did a fantastic job.
Well, thank you so much. I really appreciate that.
Yeah.
It was a fun project.
Yeah. Okay. And then we also have a question from Garrett Romaine, who's asking if you're going to be up in the area to sign copies.
So as of right now, I don't have plans to travel to Oregon again. However, I do have a number of sticker book plates. So if people in the organization are interested in having a signature for their copy, what you can do, I would ask that the club organize this rather than contact me directly. It's basically figure out how many people would like a signed book plate, and then I can send that number to someone in the organization who can then distribute them to the members. So that would probably be the best way to go about that. I was trying to work out an event with the Rice Museum, but it never really came together. So it looks like I'm not going to be up in that area for now. So, which is too bad. I'd love to see you.
I know. Okay, I don't see any more questions in the chat box, but again, folks, you're free to do that. I think I'm going to stop the recording at this point. And so let me go ahead and do that.